Hello everyone, this is the Mole Made Simple with Miss Rodriguez, and today we're going over everything you need to know about the mole unit in high school chemistry. So today we're going over molar mass, percent composition, empirical and molecular formulas, one-step mole conversions, and two-step mole conversions. But what even is a mole? A mole is a unit of measurement used in chemistry to measure large quantities of very small things, so things like atoms, particles, or molecules. Molar mass is the mass in grams per mole of a substance, and we're going to use this relationship, 1 mole equals the molar mass in grams, whenever we do our conversions. And where we get this molar mass is from the periodic table. So here we have the element tile for hydrogen and carbon, and using the mass number, we can see how many grams of that element we need for there to be 1 mole of that element. So for example, for hydrogen, we would need 1.008 grams of hydrogen to have 1 mole of hydrogen. For carbon, we would need 12.011 grams of carbon to have 1 mole of carbon. And a mole is just a quantity. So just like how when we say dozen, we know that we're talking about the number 12, or when we say pair, we know that we're talking about the number 2. Same thing with a mole. It's associated with a number, which we'll talk about later. When you have an element, it's pretty easy to just look on the periodic table, but when you have a compound, molar mass has to be calculated. And this is how you calculate molar mass. So if we were looking for the molar mass of CO2, the mass number for C on the periodic table is 12.011. The mass number for O on the periodic table is 15.999. There's 1 carbon, so times 1. There's 2 oxygens in CO2, so times 2. When we multiply those numbers, we get 12.011 and 31.998. We add up those two numbers and we get our total, which is a molar mass of 44.009 grams per mole. And grams per mole is the unit that we use for molar mass. Once you have the molar mass, then you can calculate the percent composition. The percent composition is the percent by mass of each element in a compound. So for example, in K2CrO4, 40.3% of the mass comes from K, 26.8% of the mass comes from Cr, and 32.9% of the mass comes from O. Remember that percents mean out of 100. So your percent compositions, when you add them up for all of the elements in that compound, they should always equal out to 100%. Percent composition can be calculated using a formula. The formula is percent composition equals the mass number of the element times the number of atoms divided by the molar mass of the entire compound, and you multiply by 100 at the end to turn it into a percent. For example, if we try to find the percent composition of Cl and O in Cl2O7, to find the percent of Cl, we take the mass number for Cl, which is 35.453, and again, we find that on the periodic table, times 2, because there are 2 Cls, divided by the molar mass of the entire compound, which I showed you on the previous slide how to calculate, but the molar mass for this compound is 182.90. Multiply by 100 and you get the percent of Cl, which is 38.76%. To find the percent of O, you take the mass number of O, which is 15.999, again from the periodic table, times 7, because there's 7 O's in the compound, divided by the molar mass, 182.90, and you multiply your answer by 100 and you get percent of O, which is 61.24%. Once you have your percent composition, there is a way to use that percent composition to calculate your empirical formula. An empirical formula is the formula with the smallest whole number ratio. That means it's the smallest version of your compound. The molecular formula is the formula with the actual number of atoms of each element. For example, 1 over 2 is the same thing as 50 over 100. but 1 over 2 is the smallest possible version of that ratio. So that would be like your empirical, while 50 over 100 is your molecular. Some examples of molecular and empirical formulas. N2O4, the number 2 and 4 can both be divided by 2, so the empirical formula would be NO2. H2O, the number 2 and the number 1, the biggest number that you can divide both those numbers by is 1, so H2O is still H2O when we're trying to find the empirical formula. For C6H12O6, 6 and 12 can both be divided by 6, so the empirical formula would be CH2O. So again, the smallest whole number ratio, so the subscripts can never be decimals. This is how we use the percent composition to figure out the empirical formula. We have a mystery compound and we don't know how many atoms of each we need in order to get these percentages. But we know that we have C, H, and O in the compound. We know that 50% of the mass of the compound comes from C, 10% of the mass of the compound comes from H, and 40% of the mass of the compound comes from O. Using the following steps, you can figure out the empirical formula. Step 1. You turn your percentages into grams. So 50% C translates to 50 grams of C. Step 2. You take the grams and you divide it by that element's mass number. So for 50 grams of C, we're going to divide it by 12.011. For 10 grams of H, we're going to divide it by 1.008. And 40 grams of O, we're going to divide by 15.999. And again, these mass numbers come from the periodic table. Once you have your totals, you choose the smallest answer. So the smallest answer would be the 2.5 moles of O. Now you divide the moles of each element, so your answers from step 2, and you divide them all by the smallest moles. So take the answer for C, which is the 4.16, divide it by the smallest, which is 2.5, and you get 1.850. 9.92 moles of H divided by the 2.5, and we get the 3.968. 2.5 moles of O divided by 2.5 gives us 1. And using the answers from step 3, it tells us the subscripts of our elements. And notice that the subscripts must be whole numbers. So you're going to round your answers. The empirical formula for this mystery compound would be C2H4O, because we don't need to put a 1. The 1 is invisible. If we have the molar mass of the compound and we know the empirical formula, we can calculate the molecular formula. To do this, you just follow the steps below. So step 1, you multiply the subscripts from the empirical formula by the molar masses. So for C, there were 2 of them, times the mass number from the periodic table, so times 12.011 gives us 24.022. Same thing with H and same thing with Cl. Then you add all of those numbers up and it gives you the molar mass of the empirical formula, which in this case is 60.4 grams per mole. Step 2, you take the molar mass of the molecular formula, so that was the 181.5 grams per mole, and you divide by the molar mass of the empirical formula, so 60.4 grams per mole, and in this case we get 3. And you use that number as your multiplier. So you take all of the subscripts from the empirical formula and you multiply it by your multiplier. In this case, we're multiplying all of the numbers by 3, and we get our molecular formula, which is C6H3Cl3. Now let's go over one-step mole conversions. If you don't know how to do dimensional analysis yet, I would highly suggest that you pause the video and you go watch my other video about chemistry math. It has the basics of dimensional analysis in there and will help you greatly when you're trying to do mole conversions. Dimensional analysis is just a way to set up your calculations so that your units cancel and you're able to turn one unit into another. Moles is just a count, meaning it represents a number. So just like how when we think of the word dozen, we think of the number 12, when we think of moles, we need to think of a particular number. And just like how we're able to use dozen to convert into other units, we are able to use moles to convert to other units. So in this example, we have 6.5 dozens and we need to figure out how many eggs that is. If we have dozen on top, we want dozen next at the bottom, so 1 dozen. And we know that 1 dozen is equivalent to 12 eggs. So 1 dozen, 12 eggs. The dozens cancel and you're left with the unit you're looking for, so we're left with eggs. And now all we have to do is calculate. You multiply your top numbers, divide by your bottom numbers. So 6.5 times 12 divided by 1 gives us 78 eggs. So 6.5 dozen is equal to 78 eggs. Just like dozen, pair, a mole is also a unit of measurement. There are 3 things that we can turn moles into. We can go from moles to gram, moles to liters, or moles to Avogadro's number, which is used for molecules, atoms, or particles. First, let's go over moles to gram. The relationship between moles and grams are 1 mole equals the molar mass in grams, and we just went over how to calculate that molar mass. For example, how many moles are in 2.8 grams of H2O? We start with what we know and what we want. So we know we have 2.8 grams of H2O. We want the moles of H2O, and we know the relationship between them, right? 1 mole equals molar mass. We know that the molar mass of H2O is 18.015 grams per mole. And again, we calculate that molar mass by multiplying how many times the number from the periodic table for each of the elements and adding them up. Now that we have our relationships, we plug it into the dimensional analysis format. Starting with what we know, 2.8 grams of H2O. If you have grams of H2O on top, you want grams of H2O next at the bottom. And remember that grams comes from the molar mass. So molar mass of H2O, which is equal to 1 mole of H2O. And moles is what we're looking for, so we can stop. Multiply your top numbers, divide by your bottom numbers. So 2.8 times 1 divided by 18.015 gives us our total, which is 0.16 moles of H2O. And that's how you go from moles to grams. Now let's go over how we go from moles to Avogadros. So remember how I said that moles are associated with a particular number? This is the number for moles when we're talking about atoms, molecules, or particles. 1 mole is equal to 6.02 times 10 to the 23. And that's true for anything. So 1 mole of anything is 6.02 times 10 to the 23. Just like how 1 dozen of anything means 12 of that thing. If I say there's a dozen planets, then you know I'm talking about 12 planets. Same thing with the mole. 1 mole of anything is 6.02 times 10 to the 23. So 1 mole of hydrogen, which is equal to 1.008 grams of hydrogen, contains 6.02 times 10 to the 23 atoms of hydrogen. 1 mole of oxygen, which has a mass of 15.999 grams of oxygen, contains 6.02 times 10 to the 23 atoms of oxygen. 1 mole of H2O, which has a mass of 18.015 grams of H2O, contains 6.02 times 10 to the 23 molecules of H2O. For our example, how many atoms are in 3.2 moles of sulfur? We know we have 3.2 moles of sulfur. We want the atoms of sulfur, and we know the relationship between moles and atoms. Plugging it into our dimensional analysis, starting with what we know, 3.2 moles of sulfur. If we have moles of sulfur on top, we want moles of sulfur at the bottom, and we know that 1 mole of sulfur is equal to 6.02 times 10 to the 23 atoms of sulfur. Multiply our top numbers, divide by our bottom numbers, and we get 1.93 times 10 to the 24 atoms of sulfur. Now that we've gone over grams and avogadros, the last thing that we can turn moles into is liters. And the relationship between moles and liters is 1 mole is equal to 22.4 liters. For our example, how many moles are in 15.1 liters of H2? We know that we have 15.1 liters of H2. We want the moles of H2, and we know the relationship between moles and liters. We plug into our dimensional analysis, starting with what we know. So 15.1 liters of H2. If we have liters of H2 on top, we want liters of H2 next on the bottom. And again, it's always 22.4 liters when we're equating it to 1 mole. So 22.4 liters of H2 is equal to 1 mole of H2. Multiply your top numbers, divide by your bottom numbers. So 15.1 times 1 divided by 22.4, and we get our total, which is 0.67 moles of H2. Now we can take it one step further and do a two-step mole conversion. For example, how many liters are in 4.8 atoms of oxygen? We know that we have 4.8 atoms of oxygen. We want the liters of oxygen, so we can use the mole as a bridge to go between atoms and liters. We know that both of them do have a relationship with moles. So 1 mole equals 22.4 liters, and 1 mole is also equal to 6.02 times 10 to the 23 atoms. Using those relationships, we plug it into our dimensional analysis, again, starting with what we know. So 4.8 atoms of oxygen. If we have atoms on top, we want atoms next at the bottom. Remember, the number associated with atoms is 6.02 times 10 to the 23, which is equal to 1 mole. If we have moles on top, we want moles again at the bottom. And 1 mole is equal to 22.4 liters. Liters of oxygen is what we're looking for, so we can stop. Notice how I didn't stop at moles because moles is not what the problem was asking for. It was asking for liters, that's why I took that extra step. Multiply all of the top numbers, divide by your bottom numbers, and we get our total, which is 1.79 times 10 to the negative 22 liters. All right, that is everything that you need to know about the mole unit for high school chemistry. Thank you so much for your time. Let me know if you have any questions in the comments below. If you found this video helpful, make sure you hit that like button and subscribe so you don't miss any of my future chemistry content. I will be creating and releasing videos soon that have more step-by-step examples about moles. If you're a chemistry teacher and you would like access to this exact PowerPoint, it is on my TPT store called Chemistry Made Simple, as well as worksheets, labs, and activities that align with this unit and all other units of high school chemistry. I hope you have a great day. Bye!